Thanks for the introduction. So today I'm happy to present two recent work in my group, EAGLE and EAGLE-2. And their purpose is to achieve lossless inference acceleration for large language model. So we want to inference the large language model inference. And before that, let's look at how vanilla autoregressive inference works so that we can know what is the drawback in the vanilla inference, and then how can we solve this bottleneck? How can we solve this drawback? So let's say we are given a large language model, which consists of several layers, an embedding layer, which can map a given token to an embedding vector, followed by several transformer layers. They are the combination of attention layers and FC layer. And then followed by an LLM head. You can view the LLM head as a mapping from any feature vector to a distribution so that we can sample the next token from this distribution to get our prediction. So typically LLM head, you can view this as just an FC layer. So when we do the vanilla inference, we are given a prompt. Let's say in this case, the prompt is a single token, how. We input this token into our embedding layer. We get the word embedding, yi-how. And then we input this yi-how into our transformer layer, and we do the attention, and followed by FC layer. We get the feature vector, f-how. And we can input this f-how into the LLM head. We get a distribution. So we use this p-how, or say this blue distribution, to denote the distribution predicted by the large language model. So from this p-how distribution, you can choose whatever sampling methods you prefer, such as greedy sampling, non-greedy sampling, or even the beam search. And then you can get to the next token. This is your predicted next token, can. And with the can, the new token, you can put this back to the bottom, and you input this new token into the embedding layer. You get the word embedding, yi-can. And then you can input both yi-can and this yi-how in the previous round into the transformer layers. So you want to do the attention between yi-how and yi-can, and you can get the prediction for the can token, that is f-can. And with f-can, you can input this vector into the LLM head. You get the distribution for the can token, that's denoted by p-can. And after sampling, you get the next prediction, next predicted token, I. So you just repeat this procedure. You input the I into the bottom, and you input, you're moving forward, you do the forward pass until finally, you do this again and again until finally you will encounter this EOS token. That being said, your generation is finished and you should stop. So from this vanilla autoregressive inference pipeline, we can find that here, in terms of the generation, each token is generated one by one. So we need to generate the second token before we can get the third token, and so on and so forth. So we can see this is a sequential inference. However, modern GPUs, they are good at parallel computing. So the question we want to answer in this talk is that whether it's possible to transfer this sequential inference to a parallel computing pipeline so that we can achieve inference acceleration. So to do that, we want to consider a framework called speculative sampling, and some people also call this speculative decoding. And there are two modes in this framework. One is the draft mode, another is the checking mode. So in the draft mode, let's assume that we are given a good approximation of the original large language model, denoted by a tiny model, this yellow module. And we want to use this tiny model to guess the tokens generated by the original large language model. So we do the vanilla autoregressive inference for this tiny model. Given the same prompt, how, we input it into the tiny model, and we get the output distribution by the tiny model. Here we use q-how, or see this yellow distribution to denote the distribution predicted by the tiny model. So we get the output distribution. We can do the sampling. We get the next token, the second token by the tiny model. And we can put the second predicted token can back to the top. We input the can into the tiny model. We get the distribution for the can token. That's denoted by Q can. And we can do the sampling. We get the third token V. So this is a draft model. So we draft mode. We can see by this procedure, we can get a set of, or say a collection of tokens drafted by the tiny model. But one may observe that this procedure is still a sequential inference. So it cannot use the parallel computing ability of modern GPUs. However, we also notice that the tiny model is very small. So in terms of the inference, it can also be very fast. So this draft mode will not take too much time because the model is very tiny. So after we finish the drafting, that being said, we have the tiny model, and tiny model predicts a collection of tokens drafted by this tiny model. How can we? And the second mode in the speculative sampling framework is a checking mode. So we want to involve the original large language model to check the correctness of these drafted tokens. And because this three tokens, this set of tokens drafted by the tiny model are already available to the original large language model. So the benefit here is that in this checking mode, we can check everything in parallel. We can check the correctness of all these three tokens in parallel. So that can take advantage of the parallel computing ability of modern GPUs. So for this, how can we do the parallel checking. So that being said, we input the how, can, and v simultaneously into the embedding layers. We get their word embeddings respectively, EHAO, ECAN, and EV. And then we input EHAO, ECAN, EV into the transformer layers, and we can do the attention. And after FC layer, we get the feature vectors for these three tokens, FHAO, FCAN, and FV. And after the LLM head, we can map this feature vector to two distributions. They are PHAO for the token HAO, and PCAN for the token CAN, and PV for the token V. So we use this P to denote the distribution by the large language model. And then we want to compare this distribution with the distribution from the tiny model denoted by QHAO. So this QHAO has already been accessed in the previous drafting mode. So we want to check the, because we have the how can we. So as of the first token, we want to check the correctness of the second token can, because how here is our prompt, and we want to check the correctness of can. So let's say we set the current token T as this can token, and we want to follow a two-step checking mode. In the first step, let's say we flip a coin. We sample a random value uniformly from interval from 0 to 1. And if this value that's denoted by R is less than mean 1 P divided by Q, where T is our current token can, if this holds true, then we will accept this token can. And this mean 1 PT divided by QT is also known as the accept rate. And the first token is accepted, and then we want to check the second token V. And we set the T as a V, and we want to check whether we sample another R from this uniform distribution, and we want to check whether this R is less than mean 1 PT divided by QT, where T is the third token V. And if this holds true, we want to accept this token. But suppose this does not hold true, then we want to go through the second branch. That being said, we want to correct this V token to a new token, T prime, which is sampled from a normalized distribution of max 0, P minus Q. So that being said, we want to sample another T prime to correct this V, let's say to a new token I. So this norm distribution is also known as a correction distribution. And because the second token is not accepted, so we will also not accept the third token as well. So that is the checking mode in the speculative sampling framework. So there's a theorem to guarantee the correctness of this checking mode. So the theorem tells us in these two papers, the theorem tells us the above PQ sampling procedure is equivalent to sampling from the P. So intuitively, that being said, we have the P distribution denoted by this red distribution. We have another Q distribution denoted by this purple distribution, where P is a distribution by the large language model, and Q is a distribution by the small drafted model. And all speculative sampling framework is all about how to use the sampling from this PQ, these two steps, to mimic the sampling from P. And when P and Q are closer, that being said, the distribution from the large model is almost the same as the distribution from the small model. And that being said, the drafted model will guess more accurately, and we will get a higher accepted rate, and that will lead to higher speed-up ratio. So that's why speculative sampling is all about how to make P and Q distribution to be closer. But how can we build the tiny model Q? So we have the P because P is the distribution by the large model. But how can we build the tiny model Q? In this framework, they assume Q is given, but how can we build that in practice? So that is also the question we want to answer in this talk. So how to build a tiny model Q? We should be careful about intrinsic trade-off between accuracy and efficiency. If we choose a tiny model Q to be very small, the inference for the draft can be very fast. However, it will bring inaccurate prediction. So that being said, most of the tokens predicted or drafted by the model Q will not be accepted by the large model P. And on the other hand, when we set the Q the same large as the original large language model P, the prediction can be very accurate. So most of the tokens drafted by Q will be accepted by the large model P. However, the draft mode can be very slow. So we should be really careful about balance the trade-off between this accuracy and efficiency issues. So to resolve this issue, we propose EAGLE-1. And this is a joint work with Yuhui Li, Fangyu Wei, Chao Zhang, and myself. And this is a publication in ICML 2024 in this year. So here is our motivation, or say our observation. So suppose at this time, we are given a prompt which consists of 3 tokens, how can I? And we input them into the embedding layers. We get the word embedding, 3 word embedding, Yihao, Yikan, and Yi. And if we look at the evolution path, or say the PDE path from Yihao to Yikan and Yikan to Yi, we find that the dynamic, this Yihao to Yikan and Yikan to Yi, the dynamic can be quite complicated. So that being said, in order to overfit this evolution path, you need a super large model to do that. However, if we look at the top layer, being said, you do the forward pass, you input Yihao, Yikan, Yi, continue into the transformer layers, and you get the 3 feature vectors, F-Hao, F-Kan, and Fi. And if you look at the evolution path as the top layer from F-Hao to F-Kan and F-Kan to Fi, you find that the dynamic can be very simple. And that being said, in order to predict the future feature vector, it can be very simple. You only need a tiny model to do that. So that motivates us to, instead of doing the next token prediction, let's try to do next feature prediction. And that can lead to a better accuracy, better acceptance rate. So this is our first try. This is not a complete version of EAGLE-1, but this is our first try. So let's say we are given the original large language model and we freeze all their parameters, including the embedding layers, transformer layers, and the LLM heads. And let's say we want to train a tiny model, single transformer layer. You can view this as our draft model. So given the three tokens as our prompt, how can I? We input them into the embedding layers. We get the word embedding, yihao, yikan, yi, and input them into the transformer layers to do the attention. We get the feature vectors, fhao, fcan, and fi. And in the next step, let's say we input this fhao, fcan, and fi into the single transformer layer we want to train so that we get outputs. And this output should be a vector. And let's view this vector, this output, as a prediction of the feature vector of the next token. Let's call this fhelp. And after we get this fhelp, we input it into the LLM head. We get a distribution. And after sampling, you can sample the next token u. And fhelp is our prediction. And in the next step, we also want to input the fhelp into the single transformer layer to do attention together with fhao, fcan, and fi. So you input these 4 vectors into this single transformer layer, and you get the output. And the output should be the prediction of the feature vector of the next token. Let's call it fu. And with fu, you can go through the LLM head, you get the distribution, and after sampling, you can sample the next token. Then you just repeat this procedure together. You input fu also into the single transformer layer, and by keyword cache, you can also do the attention with fhao, fcan, fi, fhelp, and you get the prediction for the next token, f question mark. And you do the sampling, you encounter EOS, then you stop. So these 2 figures show the power of this idea. So this idea of doing the next feature prediction, where the left figure is for the speed up ratio, the right figure is for the acceptance rate, or say the accuracy, and the yellow curve here is for the next token prediction to do the draft, and the green curve is for the next feature prediction to do the draft. So we can see in terms of both the accuracy and the speed up ratio, next feature prediction is significantly better than next token prediction. However, this idea, this implementation is still not perfect because of so-called feature uncertainty issue. Let's say let's look at this example. Let's say our first prompt is I, and we want to predict the next token. So we input this into the model, we get the feature vector, and after the LLM head, we can get the probability for the next token, the second token. For example, with probability 0.6, the second token is M, and with probability 0.4, the second token is always. Then we can do the sampling. We can either sample the second token as I am, or say sample the second token as always. So we get 2 branches. And depending on whether the second token is M or always, it will decide what is the third token. For example, suppose the second token is M, then we can see if we look at the prediction for the third token, we can see the probability 0.3, the third token is excited, as with probability 0.7, the third token is ready. So that being said, if the second token is M, we have two choices, excited and ready. But it's almost impossible for us to get the third token to be begin or loop if the second token is M. And similarly, suppose the second token that we sample is always. Then if we look at the third token with probability 0.8, the third token is begin. And with probability 0.2, the third token is loop. But with probability 0, the third token can be excited already if the second token is always. However, in this next feature prediction, we do not use this information because here you can see we only input the feature vector into the single transformer layer. but we do not consider whether the token, this sample token is help or not, or what is the token that we sample in the previous round. So we do not use this information. For example, we do not know whether we go through the above branch or bottom branch. So that's why this next feature prediction has this feature uncertainty issue. So to resolve this issue, the idea is that how about we also involve the sampling information into our prediction of the next feature. So we have originally we use Fi to predict F always, but here in order to resolve this feature uncertainty issue, we also want to concatenate this Fi with the word embedding that we sample in the last round. For example, in the last round, we sample always as our second token, and we get the word embedding E always. And we want to concatenate Fi together with E always to be a longer vector. And we use this longer vector to predict our next feature F always. So using this idea, we can see in terms of the speed up ratio and acceptance rate, feature plus shifted token always doing the best. We can even get the accuracy roughly 0.8. And in terms of the speed up ratio, we can get roughly 3 times speed up compared with the green curve and the red curve here. So this is how we do that. With that, we get the EAGLE, and here is how we do that. So in EAGLE, we have the original large language model. We have the frozen embedding layers, transformer layers, and LLM heads. We freeze all these parameters. And we also want to train a draft model. So the trainable part is given by this yellow module. And we also copy the embedding layer and the LLM heads from the original large language model to the draft model. So these two, they share the weights, and these two, they share the weights. And we freeze all these parameters while we only train this single transformer layer. So let's say our prompt is how can. We have 2 tokens. And we first use the large language model to do the inference. We input how and can these 2 tokens into the embedding layers. We get the word embedding, yi hao and yi can, respectively. And we input them into the transformer layers, and we get the feature vectors f hao and f can. And we input f hao and f can into the LLM head. We get the distribution. And after sampling, we get the next token I. So this is the generation tree. So prompt is the root is the query, how can. And as the first token that we generate, we get the I. And as the next step, we want to copy the f how and f can that we already get to the bottom of the draft model. So we have for the f how and f can. And the first token that we generate is I. So we also want to copy the I here as the bottom. And the second token is can. So we also copy it here. So we input the can and I into the embedding layers. We get their word embedding, yi can and yi. And we want to concatenate it with the feature vectors that we get. We concatenate it with the f how and concatenate ei with f can. And we get a longer vectors, f how, yi can, as our first vector, and the second vector is f can, ei. Then we input both of them into the single transformer layer to do the attention, and we get the next feature prediction. It's fi, so we use the red bounding box to denote this is a predicted feature vector. So with fi, we input it into the frozen LLM heads, we get the distribution, and we do the sampling. And let's say instead of doing one-time sampling, we do multiple time sampling. For example, the top 1 choice for the next token is make, and the top 2 candidates is help. So we get the third token, either make or help. So we get 2 branches. The third layer is either make or help. We have 2 branches here. And we have make and help. We copy them to the bottom of the draft model. And we input them into the embedding. We get the word embedding, eMake, and eHelp. And notice that the make and help, they are in two branches. So they should be in parallel. And we want to concatenate them with the FI, the feature predicted in the last round. So we get FI and FI here. And we want to concatenate FI with eMake in the first branch and concatenate FI with eHelp in the second branch. And we input them into the single transformer layer and want to do the attention with the first token and the second token here. But notice that because make a branch and help branch, they are in parallel, so they should not do the attention with each other. So that being said, this branch, this token should be, this vector should only be able to see this vector and this vector, but cannot see this vector. And similarly, for the eHelp vector, it should be able to see EI vector, this vector and this vector, but should not be able to see FI and eMake vector because they are in two branches. They should not see each other. And you do the attention and you get the prediction for the next token. You can, the prediction for the next feature, you get fMake, fHelp, and you input them into the LLM head, you get the distribution, and after sampling, you can sample the next candidates. For example, when the third token is make, you can see the next candidates can be either a or our. So here we do the 2-time sampling, we get the top 2, top 1 is a, top 2 is our. And similarly, if we go the right branch, if we look at the fourth prediction, we can the prediction in the fourth layer, the prediction can be either with or u, where with is our top 1 choice and u is our top 2 choice. Then we can just repeat this procedure. Let's say we want to we look at this branch and we have with and u, and we want to concatenate them with fHelp. We want to do the attention, and after doing that, we can continue expand this tree to the 5th layer. For example, the, your, or to, or few. So that is how we do the inference in the EAGLE. And in terms of the implementation, we call this a tree attention. And we can see here, by this procedure, we can generate a tree because we typically here we do the multiple we do the sampling multiple times, we get a tree. Where the root is a query, and each layer means that the second layer is the second token that we generate, and the third layer is the third token that we generate, and so on and so forth. And we want to, in terms of representation, we want to flatten it to a one-dimensional vector, where the first element is the root node, it. The second element is the second layer, is and has, and then the remaining tokens can be the remaining elements, the two would be. And also we want to make sure that each node can only see its ancestor. For example, for this token it can only see itself, it can only see is, it can only see it, but this token, this node cannot see the or cannot see to. And this is implemented by the quorum attention mask, for example, here. For this token it can only see itself, can only see its father, and can only see its grandfather, but it cannot see other branches or other nodes, such as their brother or sister. So that is how we implement the tree by coding. And in terms of the number of parameters of the draft tree, the draft model, it can be very simple. It can be very small. So here we only train a single transformer layer, and because for the original large language model, the more parameter we have, that being said, the dimensionality of the feature vector can be longer. And here in EAGLE, because we also concatenate the vector, so that being said, the concatenated vector can be even longer to double the dimensionality. And so that's why the number of parameter in the single transformer layer should also be larger. So that being said, the larger the original large language model is, the larger the draft model should be. And here is a comparison between the number of parameters in the original large language model and the number of parameters in the draft model. So when the draft model is 7 billion, the number of parameters in the draft model is 0.24 billion. And it counts only as 3.4% of the number of parameters in the original large language model. And when the original large model is 70 billion, the number of parameters in the draft model is roughly 1 billion, and it counts as 1.4% of parameter of the original large language model. And for the EAGLE, everything is trainable on some cheap GPU, such as RTX 3090 on Share GPT for 1 and 2 days. And here is the performance on the empty bench evaluated by our group. So we compare EAGLE with some previous state-of-the-art, such as Medusa, look ahead, denoted by the red bar, also vanilla speculative sampling. And we can see EAGLE doing the best. In particularly on the empty bench, EAGLE is 3 times faster than vanilla decoding, denoted by this yellow bar. 1.6 times faster than Medusa, 2 times faster than look ahead. And more importantly, because of the theorem that I mentioned before, EAGLE is provably maintaining the text distribution, meaning that we will not suffer from any quality loss. And we get the inference acceleration for free. And here is this right video shows a comparison between EAGLE, Medusa, look ahead, and vanilla by the same prompt. And here we use a greedy sampling to make sure that the generated contents are exactly the same to do a fair comparison. And we can see for the EAGLE, the speed up is roughly 30 tokens per second, while Medusa is 18 tokens per second, look ahead is 11 tokens per second, and vanilla is the slowest one, is roughly 8.6 tokens per second. So EAGLE doing the best, also in this demo. And for third-party evaluation, so this is a paper published on EMLP finding this year. And they built a benchmark called Spect Bench, and they evaluate all speculative sampling method in the literature by a rigorous experimental comparison. And they do the experiment on either RTX 3090 GPU or A100 GPU in terms of 6 aspects: translation, multi-turn conversation, RAG, mathematical reasoning, question answering, and summarization. And EAGLE doing the best. So EAGLE is denoted by this blue bounding box. And so this is a benchmark on Vicuna 7 billion. EAGLE can achieve 2.1 overall speed up ratio. And on A100 Vicuna 7 billion, A100 Vicuna 13 billion, and A100 Vicuna 33 billion, EAGLE is always doing the best in this benchmark. So that is EAGLE-1, but we find that EAGLE-1 is still not perfect. So that's why we recently also released EAGLE-2. This is also the joint work with Yuhui Li, Fangyun Wei, Chao Zhang. And this is a publication in EMLP 2024 in this year. So the problem in EAGLE is basically its lines on its use of static tree structure. For example, when let's say the prompt is 10 plus 2, and we want to guess the next token. And in EAGLE, we always use a tree structure. So we always generate 2 branches. So we can see for the next, to guess the next token, it can be either equal or plus. And this is reasonable because if you give a human 10 plus 2 and want human to guess the next token, we are not sure whether the next token should be equal or plus, so we should treat them equally. And that is also what we do in EAGLE-2. However, if we modify the prompt a little bit, let's say At this moment, the prop is 10 plus 2 equal. And if you ask a human, what is the next token? So in that moment, the human must say the answer should be 12. So the next token should be 1, and the next token should be 2. However, if you look at the EAGLE, because they always build a static tree structure, so if you ask EAGLE to build a tree, it will generate 2 branches, where the first branch is 1 and the second branch is 3. However, to our human, we know that this 3 is impossible to be the next token. So that's why we want to modify that, because the build of this 3 token as a draft will also waste some computational resources and make the speed up ratio to be smaller. So in EAGLE-2, instead of using a static tree structure, we want to build a context-aware tree structure. So that being said, we want to build a tree as this structure, where because we know the next token must be 1, so we only use 1 branch as our next prediction, and then we followed by the next token, which is 2. So this experiment shows the benefits of dynamic tree structure, or say the drawback of the static tree structure. Well, let's say the root is a query, and let's have a 2-branch tree, where this position is P1, the top left corner is P1, the top right corner is P2, followed by P3, P4, P5, P6. And we want to calculate the accepted rates for each position. So here we have 1, 2, 3, 4, 5, 6, corresponding to P1, P2, P3, P4, P5, P6. And we sample a lot of query, and we calculate the accepted rates. And the accepted rates is given by speculative sampling mean 1P over Q. So this is what we claimed before. And we find that from this experiment, the position 1 typically have the highest accepted rate, while the position 6 typically suffer from the lowest accepted rate. So that being said, typically we prefer to accept the token in the top left corner and want to reject the token at the bottom right corner here. So that's why we want to prune this tree to be a simpler tree so that we can save some computational resources. But how can we determine the importance of each node? And as we mentioned here, definitely we want to use the accepted rate, which is given by mean 1 PT divided by QT, where P here is the distribution from the original large language model. However, in the draft mode, we cannot get access to this P. So in the draft mode, we cannot calculate this accept rate exactly. So we want to find an approximation whether we can use Q to approximate this accept rate. A good news is that indeed we can use the confidence of the draft model Q as a good approximation. And this experiment supports our hypothesis, where the x-axis, let's say, referred to the confidence of the draft model Q, and the y-axis referred to the accepted rate, mean 1 PT divided by QT. And we find that they are highly correlated. So you can see we can find a line to predict the relationship between confidence and the accepted rates precisely. So that being said, these two measures, they have a strong linear correlation. So we can use the confidence of the draft model Q as a good approximation to estimate the accepted rate, to decide whether we want to prune a node or not. That leads to a context-aware dynamic draft tree. So here's an example. Let's say we use a beam search with top 2. And the query is our root. Let's see, the query is it. And for the root, we set the importance as 1. And given the draft model will give us the next token prediction, the probability for the next token. For example, with probability 0.6, the second token is, and with probability 0.2, the second token is has. So in order to set the importance for this is node, we want to multiply 1 with 0.6. So we want to set 0.6 as the importance for this node. And similarly, for the importance of has, we want to multiply 0.2. This is from the draft model with this 1, and we get 0.2 as the importance of this has branch. And then we want to moving forward, and the draft model want to continue predict the third token. Given it and is, the next token is with probability 0.8, and the next token is the with probability 0.1. So we want to set the importance for this node by 0.6 times 0.8, which is 0.48. And similarly, we want to set the importance for this the node as 0.6 times 0.1 from the draft model to, and we get 0.06 as the importance of this. And similarly, we can set the importance for this two nodes and a node. And because we are doing the beam search, and for this layer, we have 4 choices. So we want to choose the top 2 for this layer. We find that and 2, they are with the top 2 choice. So we want to continue expand these 2 nodes, and 2, to the next, to the 4th layer. We get a good, a nice, or B and a D. And we can also set the importance for this good as 0.7 times 0.48. And we get 0.34, and we set this as the importance of this good node. And similarly, we can set the importance for nice, B, and do. So we get a tree, and finally, we want to do the re-ranking according to their importance, and then we choose the top 8. For example, the blue bounding box is with the top 8 importance, so we want to keep them, and we want to delete the black or say the green nodes, do, and nice. And for the blue bounding box, we also want to flatten them to one-dimensional case, similar as EAGLE-1. And we also want to set the corral masking attention mask similarly to EAGLE-1. For example, this node can only see itself, can only see its father, and can only see its grandfather, but this node cannot see its sister or brother. So we want to show that, we want to reveal that in the corral attention mask. So that is the EAGLE-2. EAGLE-2, we use, we design a method to get a context-aware dynamic tree. And here is the performance on the empty bench. We compare EAGLE-2 with EAGLE-1 and some other method, Medusa, look ahead, and vanilla speculative sampling for the greedy sampling case. When we set the temperature equal to 0, we can see for Vicuna, Llama 2, and Llama 3, EAGLE-2 always doing the best. And compare with EAGLE-1, we can see significant improvement here from 3 times speed up ratio to 4.2 times speed up ratio here. And for the non-greedy sampling, let's see, we set the temperature equal to 1, and we compare with EAGLE and the speculative sampling. And EAGLE-2 also doing the best. Here we do not compare with the Medusa and look ahead because in their method, they do not yet support the non-greedy sampling. So we do not compare with them here. And here is a more detailed comparison between EAGLE-2, EAGLE-1, and some other state-of-the-art speculative sampling method, SPS, PLD, Medusa, look ahead, Hydra, EAGLE-2, for the temperature equal to 0, and for the batch size set as 1. And we do the experiments on several data sets, including empty bench that we showed before. We also add human evaluation, GSM8K, a mathematical data set, Alpaca from Stanford University, CNNDM, and natural question. And we also calculate the mean for these 6 data sets in terms of the speed up ratio and the average number of accepted tokens. So for EAGLE-2, it's always doing the best. It can achieve 4 times speed up ratio compared with the vanilla decoding. And in terms of average number of accepted token, it's can achieve as high as 4.6, while the previous state of the art is only 3 or even 2 number of tokens, accepted tokens. So this is for Vicuna Llama 2, Vicuna 7 billion, and Llama 2 7 billion. And when temperature equal to 1, batch size equal to 1, we compare with the EAGLE and SPS. And for the other method, they do not support, they may not support non-greedy sampling. So we only compare these 3 methods. And similarly, EAGLE-2 doing the best can achieve the fastest speed up ratio and the average number of accepted tokens. And EAGLE-2 also can help reduce the inference cost. For example, if you run EAGLE-2 on some cheap GPUs, such as RTX 3060, which costs only $600, you can see the speed you can achieve 40 tokens per second. And you want to compare it with running the vanilla decoding on some expensive GPU, such as A100, which costs more than $10,000. And you can see EAGLE-2, even on some cheap GPU, it's also even faster than vanilla decoding on some expensive GPU. And here in this experiment, all the property is the same. And we also do the gradient sampling for a fair comparison. So this shows that EAGLE-2 can help us to reduce the inference cost. We can just buy some cheap GPU, and we can achieve the speed of some expensive GPU by vanilla decoding. And third-party evaluation, recently they updated on October 25th. They also add the same paper. They add EAGLE-2 to their leaderboard, and we can see EAGLE-2 doing the best on their leaderboard. Achieve the overall accelerates by 2.25 times speed up ratio. And EAGLE in the community, EAGLE has been integrated into many open source framework, including vLLM, NVIDIA's TensorRT LLM, and by collaborating with Intel, we have also integrated EAGLE into LLM library for PyTorch and Intel extension for transformers. And recently, EAGLE is also being merged with SGLang. Maybe next week it will be finished. And how to use EAGLE? We open source everything. So here is the QR code for our code. And you just need to import the EA model, this function, from our library. And you load the model by EA model. And you do the generation by calling model.ea generates. And then you can achieve inference acceleration. That is pretty simple. And we are also working on EAGLE-3. Please stay tuned. And in EAGLE-3, we will focus on large batch size and throughput. And as I mentioned before, EAGLE-1, EAGLE-2, they mostly focus on small batch size, such as batch size equal to 1, and focus on latency. But for EAGLE-3, we will look at the large batch size and the throughput.